Okay, so let's talk logistics for a couple minutes first, and then we will jump in and do some physics. So first of all, wash your hands. The reason we're listening to that music is number one, because it's just great. Number two, it's Bobby McFerrin's birthday, so happy birthday to him. He's the guy that sings the song. And number three, there's some like actions to do while you're listening to the song. If you don't like Don't Worry, Be Happy, find your favorite song, get your favorite 20 seconds of it, and start singing it every time you do it. It'll be great. Okay? Wash your hands. I know that Kibby said it over the announcements, but I'm going to say it again. Okay? I know that for a lot of you all, and for I'm in that group as well. Like, it's not something that will probably bring grave harm to us, but we need to protect the rest of our community, right? So if you're licking stuff and touching stuff, that's going to cause other people to get sick, and we don't want that. Chance, you're like, what am I licking? What? But I'm saying, like, wash your hands all the time. Be safe, be careful, don't spread any germs. Okay, so as you know, a number of the higher ed institutions in Iowa and all over the country have been making decisions about whether or not to reopen after spring break. ICCSD has not made that decision yet, but I would be shocked if I see you on the Monday after spring break. So here is what I know, okay? Here is what I know. I know that ICCSD is working to try and have the ability to have all students district-wide learn while we're home. I am not sure whether or not that will come down, because there are some issues at the state level that we're still trying to work through, okay? What I am telling you right now is that because you made a commitment to AP, that test is May 7th and will, in all likelihood, be on May 7th. And so what I am saying is that regardless of what you hear district-wide, on the Monday after spring break, I will reach out to you, okay, if we're not here together, okay, which, you know, it'd be great if we were here together, but if that's not the safe choice, then we're not going to be, okay, and we will figure out a way to make it work, okay. Some of it will be things like we've done for snow days, where, you know, I'll send you things to work on. We can also do like Zoom meetings where we can all have conversations together. We'll make it work. We'll do our best, okay. I've got lots of good resources, and it will be what it will be. But we've got to do what we can do, okay? I have a friend that works for College Board as a standard setter, so he's one of the statisticians. And so I sent him a message last night saying, hey, what do you know? Any whatever. And basically the response that I got was that everything as of right now is still on. Like, he does all that stuff in the summer when they're doing the scoring. And that right now nothing has changed. So May 7th is still May 7th. Now, if things get really bad, then adjustments may be made. And I will be honest, given like all the like whatever that I see and hear, I think that things are going to get a lot worse than people are thinking that they will. Do you know what I'm saying? And so I don't know, but we are going to move forward with the trajectory that we think that we're going to take a test on May 7th, and we'll be ready for it, whether you can or not take it. Question?
I don't know. Just curious. Would they do like an online?
I don't think that they have the
Like the iSense.
right, but the problem would be proctoring it.
Yeah.
That would and test security. So I don't know. I am sure that the people in Princeton are having that conversation right now. Right, that's where College Board is. But I don't know what the I don't know what the plan is. But anything I hear, I will certainly let you guys know. Sound good? Question? Yes, I know that they wanted to make the announcement tomorrow, but we still have to deal with the state, if that makes sense. So I think as soon as they can, they will make some announcement.
Can I just say, this is the end of the world. I really thought it would be a lot more glamorous. Like
I don't think it's going to be the end of the world. I think that it's going to be. I think we're going to be home for a little while.
No, I don't think we're ready.
So you mean the end of the world?
Yeah.
Oh my God! All right. Other questions? There you go. Yes, one more. Guys, shh, friends. I don't know. I think my vision for physics would be that a lot of it would be like videos and like here, go to this site or whatever. And then maybe every couple of days or something, we would get together for a little while and have a conversation. Yeah. Yeah. So, yeah. Does that make sense? Yeah. All right. Any other questions that you have? Go. That's what he was just asking. Yeah. All right, here we go. Thank you for reminding me. Okay. You guys need to be quiet, please. I see lots of answers from this table and here, but I want to make sure that we understand it. I want to talk it through. You can put your boards down. I got it. I'm not going to read through your answers. I want you to talk me through the answer. I see a lot of D, but I don't know. We got to figure it out, and I want to make sure that you understand it. So, Chance, you want to go ahead? Okay. So what kind of force is this? So we have to have the force of something on something. What's the something? Force of the road. What kind of force is it? A frictional force. I just want to make sure that we're getting all the pieces in here. Does that make sense? But I agree, right? That it's the frictional force, and that's the net force in the x direction, right? Everybody good with that? So we got to go back and make sure that we're checking in, because sometimes they'll throw other things in there that we want to make sure that we're paying attention to. Okay, go ahead. Now you can keep talking. Okay. Mm-hmm. Okay. 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 Over. Uh-huh. Okay. Okay. Okay, I missed the very last step that you did. Maybe because I was writing subscripts there. Say that one more time. Okay, so F large equals like a half. Is that what you mean? Of F small, which is, and that's our F. Is that okay? That did I take what you were saying and do it correctly from what you were? Okay. 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 Jacob, what were you exasperated about there? Mm-hmm. Okay. Okay. So did this happen to you today as well? Okay. So including today. Okay. So what is the correct answer? D. Okay. But if you're 50-50 every time, we need to figure out how to get you to the right side. Yeah?
I'm sorry, I just don't understand the last step.
From here to here. So that does not equal 4. That's wrong.
Oh, well, I understand when you got there. But,
Okay.
I don't understand.
Okay, and does the blue one make sense as well?
Yes.
Okay, so this is equal to F. Okay, and this, so basically the game is like, what's the difference between this thing and this thing? It's a factor of 2. Does that make sense?
Oh.
So this is half as big as this. So that's why I said the large one is half of the small one, and this is F, right? Because that's what we said here. They said that it's somewhere in the problem. The small car without skidding is F. So if I want to know what the force is for the large car, it's going to be half of what the small car was.
Okay.
Is that okay? Because I can say it in a different way too. If that's
No.
okay. Okay. And does that kind of, so Jacob, you got this one right, but I want to make sure that you're feeling confident about what you're doing.
Yeah.
Okay. It's like a 70% confidence there. I'm not 100% sure that you're there, but I want to make sure. So one reason that I like this, and I'm going to keep throwing these here as much as I can, is for you to have the chance to go through this. I will tell you that when you take the AP exam, when you're doing the multiple choice portion, there are 60 questions in 90 minutes. I'm 90% sure I can double check that, but I'm pretty sure, which means you have about how much time? 1.5 minutes per question. Okay? Which means that you have to think fast. And I'm not trying to scare you by saying that, but I am trying to make sure that you're aware that sometimes you're able to write this all out and kind of work through it, right? In another class, we were drawing a free body diagram and F-net equations and all these sorts of things, which is good practice, but we've got to practice these things so that it feels more natural, and so you don't have to necessarily spend 5 minutes on every question. Spencer.
Did you say this question has like lower, like same number of less?
I think that's about average. Yeah, I mean, maybe a little more work than average.
They put on like any like interpretation.
Sure. So there are very, very few calculation questions. I will tell you that the first year that this was offered and my kids took the test, I asked them how it went after they took it, and like 5 people separately told me, I brought a calculator and I never used it one time during the whole 90 minutes. Okay? Which is why I've been saying over and over and over this year, like, we do the calculation problems because they provide a lot of context, they provide a lot of like concrete manipulation, but this is the kind of stuff that they like, right? They like, if this gets bigger, how does that, like, which one of these affects it and how do they affect it and that kind of stuff. That's what they love. Because this is physics. The calculation stuff, that's just arithmetic, right? Maybe some higher level math in there too, depending on what you're doing, okay? But this is what they love. We'll keep doing them. It'll be great. All right. We are going to talk today about apparent weight. Yeah. So we're moving kind of from the circular motion stuff, we're going to end that before spring break, to applications of that, one of which is gravity, okay? Orbits and things like this. And when we start moving into that direction, we start talking about things like, what does it mean to be impacted by gravity? And what does it mean of weight? Hopefully you watched that 10-minute clip that I posted yesterday. If you haven't yet, make sure you do that before Friday. Right now, what I'd like you to do, we're going to work through a problem that is one that a set of questions that I actually made when I was a student teacher, so around a long time. But I'm going to have you come up and get it because I think it's pretty solid in terms of getting us where we need to go. So send somebody up from your table to come get these, and then we'll jump in and get started. It's true. The definition is not, yeah, you got it. All right. Yeah, right, then you'd be okay. All right, so here we go, my friends. Let's take a look at Bart. Now, Bart is in an elevator, and we've got some different scenarios here. And it's a glass elevator, so we can see in it, which is nice. And not only is it an elevator, but it's an elevator that has installed in the floor, actually not, it's just sitting on the floor, sitting on the floor, a bathroom scale. Because doesn't every good elevator have a bathroom scale? I mean, they should. So anyway, here he is. And for each of these, we're going to do 4 different things. So I'm going to go through one by myself or with you. Then you'll try one. We'll just kind of keep going that way. So we're going to draw arrows indicating the size and direction of the forces. Draw a free body diagram. Then we're going to determine the net force, whether it's 0, positive, or negative. Record the strength of the gravitational field. We'll define that in a second. And then calculate the scale reading. What is the apparent weight of Bart Simpson? All right, so here we go. Starting simple. In this case, here's Bart. He's standing still. The elevator is not moving. Quickly, friends, what are the forces acting on Bart Simpson? The force, okay, so let's do one at a time. So the force of the Earth on Bart, Fg. Any other forces acting on Bart Simpson? The force of the scale, which is a normal force, indeed. Fn. All right. How are we doing? Everybody good?
Oh, these are forces on Bart.
Force on Bart. Yes, yes. So we're trying to figure out the forces on Bart. Not 10. Good call. Yeah, because Bart is not being held by a rope, right? Yeah. So the only things that are actually pushing or pulling on Bart are the Earth and the scale.
Okay.
Yeah, yeah. And I appreciate the fact that you clarified that, because that means a lot in what we're doing. Okay. So now, what is the net force acting on Bart? Is it positive, negative, or 0? It is 0. How do you know? Not accelerating because it's standing still. All right. So here's a new word for you: the strength of the Earth's gravitational field. We haven't really talked about this idea of a gravitational field, but we are going to right now. Gravitational field really just means, in this case, how hard the Earth is pulling. And by that, I don't mean the force, but I mean the strength of the acceleration. So gravitational field, really, we can write A sub g, or we can write just little g. Okay. The Earth has an acceleration that acts on anything that is near the surface. How big is that? Okay. We're going to go with 10 because that'll make our lives easier. If you want to do 9.8 because you're a purist, I'm not going to fight with you. Okay. You can put a negative in there if you want. The negative just means that it's going which way? Down. All right. And then based on this, we should be able to figure out Bart's, and I'm going to actually ask you to put in here that this is not his weight, but this is apparent weight. What does the scale say he weighs? So yesterday, if you watched the video about weight, we know that the weight is the Earth, the force of the Earth on Mars. I want to know what it appears his weight is. Basically, what does the bathroom scale read? Can you figure that out? So we can write that out. We can say that Fn, say it again. 65 times the, what did you say? The 10? Yeah. It does read in newtons, yes. Yeah, it is, indeed. Yeah, because Fn plus Fg has to equal 0, right? Because there's net force of 0. So that means that Fn just equals Fg, which is his mass, times the acceleration due to gravity. And since we said that g was 10, that makes this pretty darn easy to say that the scale is going to read 650 newtons. How are we doing? Okay so far? Fantastic. All right. I'm going to let you do the second one by yourself. Not by yourself, but with your table mates, and we'll discuss in a sec. Go ahead. Okay, let's do it. All right. We're looking at the second column. Actually, it's the third column, second Bart column. All right, Austin, are there any forces acting on Bart Simpson as he's moving up at a constant velocity? Still the force of the Earth. Do we all agree? Indeed. The force of the Earth is still pulling which way? I'm hoping it's down because that's what I drew. Is that true? I'm going to go and just write it as FG because I'm lazy and I want to move fast. What else you got? Caden, are there any other forces acting on Bart Simpson? The normal force. Which way is that one going? Indeed. I don't know why I picked blue because you can't see it very well. Sorry about that. But it's there, I promise. All right. In this case, in the second one, it says it's moving up with a constant velocity. What's the net force? Oh, okay. What's the strength of the Earth's gravitational field? Same, right? I'm going to write 10 just because I want to stay consistent. I don't want it to look like it's changing because indeed it's not. One of the big take-home points, friends, this hasn't changed. You notice this? Okay, good. All right. And what is the apparent weight? What does the scale read? 650 newtons. You guys have heard of Albert Einstein? Yeah. One of the big things that he figured out, one of the big things that kind of is like blow your mind crazy, is if instead of this elevator being glass, if it was all enclosed, there is no way that you can tell whether you're moving or standing still if you're moving at a constant speed. No way to tell. All the physics works the same way in moving at a constant speed as it does standing still. There you go. Wait, what?
Wait, if you're
moving at a constant speed or standing still, there's no way to tell. If you can't see out, you don't know.
the only way you can tell is observing,
No, but I'm saying once you're moving at a constant speed, that's what I'm saying. All right, we got to keep cruising. That was not my point. Here we go, team. Accelerating up. We're going to do this one together. Number 3. What forces are acting on Bart Simpson? Fn. Which way does that go? And how about anything else? FG? What else is pushing or pulling on him? Does that make sense? Because you got to be able to describe anything, right? So this is the force of the scale. This is the force of the earth.
Oh, and the elevator's moving, so the scale is pushing up.
True, yes. But the scale is the only thing pushing on Bart Simpson. There's another thing we like about this, right? You have to think this through. So even though he's accelerating, hold on just a second. Even though he's accelerating, there are still only 2 forces acting on him. The earth and the scale. Hold on just a second. Can I finish this little thought in my brain? What's the net force? Positive, negative, or 0? How do you know? Yeah. F net equals MA, and if A is positive, then the F net has to be positive as well. Garrett, did you have a question? Do you want to hold on to it for a minute? Okay, sounds good. All right, strength of the Earth's gravitational field. -10. G is still -10. Okay. Even if I am accelerating upwards, if I drop my frog, still going to accelerate downward at -9.8 meters per second squared. It's true. All right. Now, this is where it gets interesting. What is his apparent weight? Let's figure it out together. Let's write it out. So Fn plus negative Fg, does it equal 0 this time? No, what does it equal? 1.2 times and m is 65. So there you go. So Fn is the scale reading is equal to the mass times 1.2 plus the mass times 10. Are you with me there? Does that make sense? I said that kind of fast. So F net equals MA. So I've got my MA here, and then I'm going to move FG over here. FG is so I've got MA plus MG. You can plug it in to get a number. Before we find out the number from Elizabeth, though, I want to ask those of you that haven't calculated it, is the apparent weight going to be greater than, less than, or equal to 650 newtons? It is going to be greater than because you're adding the acceleration up with that force of gravity. What did you get for FM? 747? 748? Is that what you, oh, you used 9.8, did you? Didn't you? Oh, what'd you get? 728?
Oh, wait, I used 1.5.
You're just picking out random numbers now. It's like, I was even being a good kid and used 10. I just figured you hadn't. All right, we doing okay? You do the next one. Accelerating down. Oh, there's that. All right. Accelerating downward, let's do it. What forces are acting? So this is not just moving downward, right? This is accelerating. So this is like when you're at the second floor and you're starting to move downward before you start moving at a constant speed. Or you're not going to accelerate downward all the time as you're moving from the second floor to the first floor. You told me some forces, but I missed it. Tell me again. Forces acting? FNFG, same things. You get it? You see how this is all the same? Yeah. Is it? Is FG bigger? I just kind of drew them. But it should be bigger, shouldn't it? Yeah. Which way is the net force? Down, negative. Gravitational field? True. Again, staying consistent with 10, but yeah. And question. What is his apparent weight? What does the scale read now? Is it bigger, smaller, or the same as 650? Smaller, right? So if you want to lose weight in big air quotes, you just take your bathroom scale and you accelerate downward on the elevator. This is why when you're riding in the elevator, and this is kind of what you're hitting at, you know that like little funky feeling that you get in your tummy? It's because you're accelerating. That's what's going on. Woo! Right? It's because your body's like, what is going on here?
When you're on like
Same. It's the same deal, right? Yeah. So what did you get for a value here for the force? 572. Do you guys agree with that? I didn't know if he was rounding to different numbers again or something. Yeah, we're getting there. Hold on. So be patient. Okay. All right. So now we're going to do the last one together. So here's the situation. Unfortunately, my dear Bart Simpson is now in an elevator, and the rope that is holding onto the elevator has torn apart. It is no longer. So now, I drew this in this way to make it clear. Probably the scale isn't going to like fall out that way, but what forces are acting on Bart Simpson? Just gravity. Now that's a question. Would the top of the elevator be pushing on his head?
No, because he's jumping
At the same, yeah.
I was saying, if he jumps out, he's in free fall, then it's possible.
You can't jump because you don't have to get anything to push against because everything's falling.
Okay, but so if you start in free fall while your feet are against the ground, you're still.
If you know.
As it falls.
Okay.
It's still going up as the elevator breaks.
Right. So we don't know. Yeah, we don't know what happened right before this. Okay. So we got to keep cruising, friends. Okay. Yeah. Question though.
No.
Are you sure?
It's like,
Okay. I'll say what I was thinking.
It's not the elevator.
I was gonna say this class. Very few
I know
questions are
you're a
on topic.
physicist, but like I was like, I wonder how you would survive
I mean, so okay, let's do this first, and then we'll come back because it's a good question. I want to answer the question. Let's do this first. Net force, positive, negative, or zero? Negative. There's only one force acting, so it's got to be negative, right? What's the gravitational field? How strong is it? It's the same darn thing every single time. And what is his? This is the big takeaway. This is the big deal here, friends. What does the scale read? Really?
Because it's not on the scale.
Oh, I guess there has to be an FN.
Yes.
Duh.
That's the whole reason we spent this time doing this whole thing was to get here. Okay. This is the big deal. Okay. If the apparent weight is zero, this is a situation in which we would call Bart weightless. Okay. So the thing about being weightless or experiencing weightlessness is number one, it's not that you don't have any mass. Bart Simpson still has mass, right? 65 kilograms. Okay. And the big misconception about weightlessness is that you're not experiencing, that people think that you're not experiencing gravity. Is he experiencing gravity? Indeed. That's
when
the
you
thing
jump
that's different.
into the air, for the time you're in the air, you're weightless.
Yeah. So when I am here, right, I'm standing on the chair. I'm going to jump off the chair right now. When I'm in the air there, I am weightless because if I jumped off the chair with a scale attached to my feet, don't know how that would work, but let's pretend. Well, then there's other stuff going on. Yeah. Like then it's all part of the same system, right? But yeah, that's the whole point, is that if nothing can measure your weight, then you are what they call weightless. Okay? Anytime that an object is in free fall, it is weightless. So we want to write this down so we don't forget it, okay? So why is Bart weightless? Because we are unable to measure his weight because the scale is falling at the same rate. No, I don't. I mean, I feel like that's a very absolute
pushing you
thing.
down while you're going. They can still wait. Why not pushing up?
Right, so you would be measuring something, and so that gets a little bit hairy, and I don't know for sure. I would say, shh, guys, listen. I wouldn't say necessarily that there is only one force, but it's basically that you're in free fall, and that any surface that would be pushing against you is falling at the same rate that you are falling at. Does that make sense? That's what we're talking about. So, Bo, you asked a question, something like, will you survive this? Okay, so when I jumped off of here, right, did I survive? I did. He's like, well, you're still here. Yeah, so I did survive because it's not very far, right? So that's part of it, is that if you're weightless for not very long, then you're okay because you're not going to accelerate that to that big of a speed, right? Yeah, I do, probably not, right? So then you think about, like, we did the math for jumping off of a table or a really high thing, and you have to bend your legs, right? Because it's all about impulse, right? Changing your momentum. We're going back, right? Going back to November or whatever that was. Yeah. And so you have to bend or you have to have some sort of, like, cushion of some sort. So like you see, like when there are people that are like stuck somewhere, like if they're up in a tree or up in a building, like fire, whatever, right? They have like those big, like almost like trampoline things with the dot in the middle. You've seen like that from shows or whatever, right? And the whole idea of that is to slow them down because while they're falling, they are weightless, right? So it's just a matter of how long you are weightless. So you have all experienced weightlessness, however briefly, right? Can you think of any people or job in which you experience weightlessness for a longer period of time?
Astronaut.
Indeed, right? So when an astronaut,
I was gonna say, like, you're
I mean, that's a little bit longer than, but not as long. But that's actually kind of an interesting transition. So let me like keep on that. So for an astronaut experiences weightlessness. Does that mean that they're not feeling the force of gravity? They're feeling the same darn force that we're feeling. I mean, it's still pulling towards the center of the Earth. If they're orbiting, no, thank you for saying that. Thank you for saying that. So I love what you just said. Okay. Where did my pen go? I don't even know.
Our velocity is like this, our velocity is like that.
She said,
Oh, it's circular motion.
Yes. So here's the Earth. And this is why we're doing this right now, right? So here's the Earth. Here's Garrett. Look, you're wearing a black shirt. Okay, so I'll draw you. There we go. Okay, so here's Garrett, and he's going to drop his apple, and it's going to go like this, and it's going to fall, and it's going to feel a force in this direction, right, FG? Right, the apple's weightless for a minute. But then if we zoom way out, oh, Elizabeth just had an aha moment there. Okay, here's my little rocket ship. Right, okay, but it's actually not firing now because it's just going to be moving at a constant speed. You with me here, friends? In circular motion. Okay, what's keeping it in a circle?
It's velocity.
It has to feel a force, doesn't it? What force is pulling it? What force has to be some? The force of the blank on the blank. This is the force of the Earth on the apple. What's the force of the what on the rocket ship? Earth on it's the same darn thing.
But then why is it going to
It is. We'll get there right after. Well, you'll watch a little video on it after break, probably, right? We'll get there. But the game is, friends, that if there was no gravity, where's this rocket ship going to go? It's going to go just like the yo-yo did. It's the same thing, which is why we're doing this right now. This is how it all fits together. So this goes around and around and around. Gravity's the thing that's pulling it in. So it's not a string. You have to fire your rockets. You have to go faster. You have to go faster than the. Well, not that. No.
But when you orbit in the wrong direction, if you like accelerate, well, I guess you have to.
So when you accelerate, you go off on your tangential velocity. Like if you accelerate to get out of orbit.
Yeah, so you wouldn't go in a straight line, but you go like this.
No, but if you want to go back to Earth while you're in orbit, like
Yeah, you fire your thrusters the other way so you can slow down, right?
Okay.
Yeah. That would be unfortunate, right? And that's why we have
But then
smart
you
people that get us there. Okay, so now, but really on the whole, it's really not. All right, so I appreciate you asking that. I want to say one other thing real quick, because we don't have much time, but I want to share this with you. So astronauts don't just go into space out there and they don't just like, hi, you're gonna be an astronaut. Go. What do they have to do first? They have to train, absolutely. And one of the things that they do to train is to, anybody know? They have to experience this, right? They have to experience weightlessness, not just for, they don't just go on the space shuttle a bunch of times, right? They have to be able to, so they do that, but then that doesn't really do that. That's just high G's. We want to have weightlessness. We want to experience weightlessness. How do you do that? Do you know?
They jump off a
Zero
thing.
G.
Airplane.
Oh.
They take an airplane. It's called the Vomit Comet. Nope. It's called the Vomit. It looks like a normal airplane, doesn't it? Yeah, it's just a.
Bad,
Huh?
Oh.
This is what they do.
No.
Looks like this. Yeah. So that's what they do. That's exactly how it works. So here's the game. So I can't really see it. This is like 28 or 26. So that's like 24,000 feet. They go up to 32,000 feet at 45 degrees. Up they go. And that takes about 20 seconds. Okay? Is that right? That can't be right. That is right, though, I think. Yeah. And then they experience from 20 seconds to 45 seconds, so 25 seconds of weightlessness. Okay? Where it's basically falling. And so that's where they're doing their crazy stuff. I have a video that we don't have time to watch today, but I'll post so you can watch it. It's just like, it's like a 5-minute thing, but it's about people doing it. So anyway, and then it goes down. And then the trajectory of this airplane doesn't just land. They copy and paste this over and
my
over,
God.
up and down and up and down. It's awesome, right? There they are,
The most extreme roller coaster.
right?